Hey y'all, this lesson is on the sampling distribution of the sample mean. And basically what that means, that's a lot of sampling words, but what that means is, when we have a population and we want to estimate the population mean because we can't necessarily gather all the data on a population because it's too big, then we pull a random sample from the population. And from that random sample, we can calculate certain statistics like the mean, and that will help us estimate what we think the population mean might be. Well, sometimes when we do that, there's something called sampling error that makes maybe the random sample that we pulled, that mean is not necessarily close to the population mean. But if we go and we pull a whole bunch of samples and we look at the means of all those samples, then we can get closer to the population mean. And when we take a picture, we take a look at the graph of all the sample means of all the samples that we pulled, we call that a sampling distribution. So we're going to hop right in. I'm going to show you that in a second from your notes. So we have a couple things here. I've already talked about the first two bullet points. I want to go over a few things just to review before we get into the lesson. So you might hear the word mean used in several different ways, and there's some things that distinguish the differences between what they are. So we have the population mean, we have the sample mean, and we have the mean of the sampling distribution. So there's three different things, they mean different things, and we use different symbols and stuff like that for them. So if you remember, the population mean is denoted by mu, and we call this a parameter. So when we find a value, not a statistic, when we find a value like the mean, median, or mode for a population, we call that a parameter. When we find a value like the mean, median, mode for the sample, we call that a statistic. Let me go back up. Population mean, the number, which is called a parameter, is fixed and it does not vary from sample to sample. So you have an entire population and the mean is the mean. It's done. And then the sample mean is denoted by X bar. We call it a statistic, and it does vary sample to sample, but it also has a predictable long-term value or behavior. You could say value, but either way. And then the mean of the sampling distribution, this is something that's new, is the mean of the sample means. So I talked about it a little bit earlier in this video. If you want to reduce sampling error, you can find the mean of a whole bunch of different samples of a population and then find the mean of the means, and that's what's called the mean of the sampling distribution. So if you remember, we have a normal distribution and it had the bell curve and we had all of our values in there, and it was based on maybe one sample. Well, the mean, the sampling distribution is a distribution of a whole bunch of samples. So we have the normal distribution, which is just a picture of one sample, and then we have a sampling distribution, which is a distribution of samples. So lots of sample, 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 but hopefully you're going to see what I mean here in a second on the next page. This example, it's not necessarily truly representative of a population because typically speaking, populations are very, very large. But for the sake of this lesson and trying to show you what we're leading to, we're going to call this basketball team our population. So even though it's only 5 players and it's not large enough, we're just going to use it to help us find the point of the lesson. So this, might not be anyway, moving on. So this is the NBA champions of 2019, and this is their starting lineup with their heights. I converted their heights to inches, and I also named them player A, B, C, D, E. I pulled this information from the website. So hopefully it's true information. I don't actually really watch basketball, love basketball, but I don't have TV, so I don't really watch anyway. Hopefully it's true. Looked it up online. It's true, right? So we're going to start with finding the population mean. And we're calling this starting lineup our population for the sake of the example. So if you remember how to find mean, I want you to go ahead and pause the video, find the mean, come back and check your answer. To find the mean, the population mean, it's the same way as just finding the mean. So you're finding the mean of the heights in inches, not the feet. So pause it, find the mean, come back, and we'll compare. When I calculated the mean, I got 78.4 inches. So that is our population mean. Now what we're going to do is we're going to take samples of different sizes and compute the mean of the samples. So we're going to be finding the mean a lot today. So you're going to get lots of practice finding the mean. So I kind of want to give you an idea of where we're going. We're pulling samples of different sizes and we're kind of comparing those samples to the population mean, and we're going to kind of see some behavior here. So we're going to start off by pulling samples of size 2, then size 3, size 4, size 5, and so on. So when I say a sample of size 2, we have a population of size 5. And so there's only a certain amount, there's a finite amount of ways that you can get samples of size 2. Now I started the table for y'all so you can kind of get an idea of what we're doing. But if we're pulling samples, we'll just pretend I'm pulling random samples. Then the only possibilities you can get here are players A and B as a sample, A and C as a sample, A and D, A and E, B and C, B and D, B and E, and then I think C and D, and then maybe D and E. Yeah. Oh, I forgot one, C and E. So you can actually use a tree diagram if you want to, just to make sure that you're hitting all the possibilities. A tree diagram is where you have all your players, and then you branch out from that. You can get B, C, D, E, and this sample represents A, B, A, C, A, D, A, E. And then from this player, we can get A, C, D, and you get the point. It gets a little spread out. You don't want to write any of the same ones twice, but at least you know that you're hitting all of the possible samples so you don't miss any. I'm going to try, I think in the notes at least I have the table. I should have just left that, sorry, in case you're writing it. Like the template for the table here so you can see how many possibilities there are, but the tree diagram is a good way to hit that. There's other mathematical ways to know how many possibilities there are, but I really don't want to get into that for this lesson. So we have samples of size 2. I have my samples pulled. I'm going to record the heights of those players. And then for each sample, I'm going to find the mean. So I want you to practice doing that. Here, what I want is, I actually, so I didn't have to keep going up back and forth. I actually wrote the heights on a piece of paper. I don't know if you can see it, on a piece of paper so that I just have them right here, because in a second, I'm also going to switch pages. And I don't have the heights anymore in front of me, so I went ahead and wrote them down so I don't have to keep going back and forth. You can do that if you want to. So in here, I'm writing the heights of player A and player B, player A, player C, D, E. So you're going to do that for each sample, and then in the next column, you're finding the mean of the two heights. So go ahead and pause it, fill out the table, and then come back and we'll compare. Okay, so these are the values that you should have gotten for your means of the samples. the sample means of the sample means. That's what I'm trying to say. So you should get these values. Make sure you're getting those, typing them in correctly. One thing I want to show you in your calculator that might save you a little bit of time, because this gets a little tedious, I will admit. If you, you can see in my calculator how I typed it in. I typed it in one line by doing parentheses, the addition, close the parentheses, and then divide by 2, because I want to tell the calculator that I'm adding first and then I'm dividing by 2 to find the mean. And then instead of typing that over and over and over again, because it's kind of annoying, you can do second enter. It'll bring up your last thing that you typed, and then you can scroll over and change any of the numbers that you want to change. Some of the newer calculators, you can actually just press up and you can go up and select whatever you've typed again. And my TI Inspire does that. I don't have to do second enter. But if you have an older calculator like I do, then you can do second enter. So you should get those. Before we move on, I know this isn't part of this problem, but before we move on, I want you to find the mean of the sample means, okay? So here's the sample means. Now I want you to find the mean of those. I'll pause it, you try it, and come back. So if you found the mean of the sample means, you should get, all right, mean of X bar 78.4. Huh. Look at your population mean. What do you see? Might be a coincidence, might not. We'll have to find out. Next question says, determine the probability that X bar, weird little thing right there, will be within 1 inch of the population mean. And what that's asking for, I put in parentheses, is it's actually asking you for a sampling error of 1 inch. So we're finding the probability that the sample means will be within 1 inch of the population mean. So the population mean is 78.4. For something to be within 1 inch of the population mean, then it needs to be between 77.4 and 79.4. That 9 got weird. So we're looking to see the probability that our sample means are in between 77.4 and 79.4. That's 1 inch below, 1 inch above. So in order to find the probability of that, we have to figure out how many of them are in that range. So we go up here, they have to be in between 77.4 and 79.4. So we go through and check. That one's out. This one's good. 79.4, that's good. I think there's only 2 of them. If I'm seeing it correctly, hopefully I am. 77.4, not 79.4. So that's too high, that's good. That's too low, too low, too high, too high. That's good, too high, too low, too low. So yeah, there's 2. So 2 of them out of 10 are within 1 inch, which is 0.2 if we want to put it in decimal. So the probability that the sample means will be, or there will be a sampling error of 1 inch is 0.2, which is about, which not about, it's 20%. Get my words right today. Okay, so we're just going to pause, we're going to hold that in our minds for a second, and we're going to try the next example. Determine the probability that the sample mean equals the population mean. So if we go here and we look at all of our sample means, were any of them equal to 78.4? No. So that's a 0. Probability of 0. Or there's a 0% chance that it will equal the population mean. That's a weird arrow. Let's fix it. There we go. Okay, now we're going to do a little bit bigger sample, a sample size of 3. And so that we're pulling samples of 3 players from our population of 5 players. So we've got A, B, C, A, B, D, A, B, E, A, B, A, C, D, and so on. So what I did there, again, you can do a tree diagram, or you can just go A, B, C, A, B, D, A, B, E, A, C, D. You just kind of work your way down and write your list there, or the tree diagram. So that's how I got those. So go ahead and pause it, fill in the table, and then come back and we will compare. All right, so if you found the means, the sample means of each sample, these are the values you should get. I went ahead and rounded to 1 decimal place because my raw data is in whole numbers. And typically speaking, you want to go 1 decimal past that. You can go more, like more is not bad. I actually really like more better because it's more accurate, but 1 is enough. So let's go down here, determine the probability that X bar will be within 1 inch of the population mean, which is a sampling error of 1 inch. Remember that that puts us between 77.4 and 79.4. So we're going through and we're seeing how many of our sample means are within that range. So let's see. Too high, that's good. Too low, that's good. Too low, too low, too high, that's good. That's good, that's good. Make sure. Yes. Yes. Yep. Yep. And yep. Okay. 1, 2, 3, 4, 5 out of, I think it's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's what I thought. 10. So that kind of shrinks down our error. When we had sample sizes of 2, we only had 2 of the values that were within that small range. Now we have half of the values within that small range. So taking larger samples shrunk down the probability of error, a larger error of 1 than 1 inch. Okay, now I want you to pause it and find the mean of the sample means, and then come back. I got the mean of X bar. I got 78.39, which I'm going to round to 78.4. Huh. That's pretty cool, right? I think that's pretty cool. Okay. So the next one, we're doing samples of size 4. And I left it blank this time. So I want you to go ahead and try to form your samples and then find the sample means. Pause it, try it, come back. So for your sample means, you should get these values. So go ahead and just check and make sure you got all the groups correct and then wrote down their values correct and got your sample means. And then the last part of the problem says, find the probability that the sampling error is 1 inch. So we're still doing, it has to be between 77.4 and 79.4. And then when you check that, we get 1, 2, 3 of them out of 5, which is 0.6. So we're shrinking even further. When we had samples of size 3, 50% of the samples were within 1 inch of the population mean. Then when we have samples of size 4, now we have 60% of our sample means are within 1 inch. So what's happening is the larger the sample size, the smaller the error is going to be, because we're getting closer to our true population mean by pulling larger samples. And then go ahead and find the mean of the sample means and then pause and come back. Take a guess. What do you think it'll be? If you had to guess, what would you think it would be? Go ahead and find it and come back. I got the mean of X bar was 78.44, which is, if we rounded, 78.4. That's crazy to me. I love that. Okay, moving on. Now do a sample size of 5. And if you think about that, if our population is size 5, then if we pull a sample of size 5, then it's just going to be our population in this case. So it would be A, B, C, D, E. That would be all of our heights. And then when we find the mean of that, we get 78.4. So this was sample. My table's sloppy. I should slow down. Heights. The mean. I get excited. Start going fast. There's my table. And then I've already kind of spoiled it. What conclusion can you make about the size of each sample and the sampling error? So if you could go ahead and pause it and summarize what I was saying, and maybe in your own words, what you drew, what conclusion you drew from that, and pause it and come back. So what was happening was the larger the sample size, the smaller the sampling error was. Or you might have said the larger the sample size, the more, the higher the probability that the sample means would be within an inch or have a, the 1 inch error. So if you can just kind of envision in your mind this range of the 1 inch of error. And in our first example, only 2 of the sample means were within that 1 inch. And then in our next example, 5 of the sample means are now within the 1 inch. And then in the sample size of 4, now 60% of them, I should say 20%, 50%, now 60% of them were within the 1 inch. So more and more and more of our sample means are getting closer to the population mean as our sample sizes get larger. And if we had an even larger population, like of 30 or 40 or 50 or 100 or whatever, if we pulled larger sample, a whole bunch of larger samples, let's say if the population is 100 and we pulled sample sizes of 10, and then we pulled a whole bunch of those sample sizes of 10, then a certain percentage of them would be close to the population mean. Then if we pulled sample sizes of 20 instead, then we would get even closer and closer and closer. So the larger your sample sizes are and the more of them that you can draw, the less error there's going to be. You're going to get a truer picture of the estimation of the population mean when your samples are larger. So it's just a better representation because you're drawing a better picture of what the population looks like. So for example, in some of my first videos, I talked about maybe the population being any student enrolled in classes at Ranger College, which is probably around, excuse me, 2,000 or 3,000 people. And I mentioned it's possible with 2,000 or 3,000 and computers to find the population mean. That wouldn't be too difficult. But let's say I'm just one person trying to figure out, based on a sample, what the population looks like. I would pull random samples of students from Ranger College. And if I pulled random samples of 5 students and I asked them, what's your favorite movie? I don't know. What's your favorite movie? Then I'd get an okay picture of the whole population. If I pulled samples of 10 or 20 or 30 or 40 or 50 or 100, the more samples I'm pulling, the more people I'm surveying, and the closer I'm going to get to what the population actually likes. So that's what that's kind of leading up to. Um, you're just going to get a better idea of the population with larger sample sizes, less error. In summary, the mean of all sample means is going to be, oh, I skipped a question. No, I didn't. The mean of all sample means is equal to the population mean. So that's lots of words. The mean of all sample means is equal to the population mean. So let's look back here. The mean of all sample means is equal to the population mean. The mean of all sample means is equal to the population mean. The mean of all sample means is equal to the population mean. So when we're sampling, when we find so many samples, when we find a bunch of samples and we find the mean of all the samples, and then we find the mean of the means, then we're getting closer and closer and closer to the true population mean. So crazy. Y'all are probably like, girl, that's too many samples. Samples of the samples of the samples of the samples. So if we look back and we just did this to all the parts, we found that the mean of the sample means was 78.4 inches. And then we know that the population mean is 78.4 inches. So are they the same? Yes. So cool. Okay. The sample, when the sample size is small relative to the population size, which we're going to go ahead and assume that it pretty much is, because typically speaking, now the basketball example was not really the true population. It was just used to help us arrive at this conclusion that the mean of the sample means is going to be equal to the population mean. So let me write that down because it's kind of weird wording. The mean of the sample means is equal to the population mean. So it's not necessarily enough to just find the mean of one sample. And that's what we've kind of been doing in chapters 1 through 4. We've been finding generating one sample, and we've been finding the mean, median, mode, standard deviation, range, all this stuff, drawing a box and whisker plot, all this stuff for one sample. Well, that's not really going to necessarily be representative of a population. So instead of doing one sample, we find lots of samples of the same size. We gather the mean of all those samples, and then the mean of the means is going to be equal to the population mean. And that can help you narrow down what the population mean is. So that's the big conclusion. That's a big deal. Now we need to make some conclusions about the standard deviation of the sample. And so when the sample size is small relative to the population size, which is pretty much going to be always, because like I was saying before, a population is generally very large. So like I mentioned with the Ranger College students enrolled in classes, that's like 3,000 people. That's really big. It would be really hard, almost impossible for me to go survey 3,000 people. So let's say I pull sample sizes of size 20. Maybe I pull 20 people from the Erath County campus, 20 people from the Brown County campus, 20 people from the, or 20 samples of size 20 of all of the 3,000 people, whatever. that's going to be small compared to the population. And so we can compute the standard deviation of the sample using this formula here, where n is the size of the samples. So the standard deviation of the sample mean is going to be equal to the population standard deviation divided by the square root of the sample size. So that's just a formula. And I could have gone through and helped you derive that, but I went ahead and just gave it to you. So they do say, technically speaking, that the sample size is small in respect to the population size if the size of the sample does not exceed 5% of the size of the population. I'm not going to make you go through and compute that. We're just going to go ahead and assume that it's small. And remember that something is considered large if it's 30 or more. So moving on. We have an example here. According to the manufacturing house statistics, the mean price of a new mobile home is, I think, they don't call them mobile homes anymore. They call them modular homes or something. Can't remember. Doesn't matter. Is $65,100. Assume a standard deviation of $7,200. So for samples of size 50, find the mean and the standard deviation of the sample mean. Now, let's think about this for just a minute. The sample is size 50. That's important. That's n. But that's not going to play into the mean. It's only going to play into the standard deviation. The mean is going to be equal to what? If I'm saying I've pulled all these samples for samples, that's plural, of size 50. I've pulled all these samples of size 50. I found the mean of all the samples. What is going to be the mean of the sample means? It's going to be equal to what? It's going to be equal to the population mean. Remember back here, the mean of the sample means is equal to the population mean. So if they tell me here that the population mean is $65,100, then the mean is going to be equal to that. And then the standard deviation of the sample mean, that's going to be where it's different. It's not necessarily going to equal the 7,200. We're going to have to use our formula. The standard deviation of the sample mean is the population standard deviation divided by square root n. So we know the population standard deviation, and we know n, and then we'll just type that in our calculator. 7,200 divided by square root 50 is about 1,018.2 dollars. So for samples of size 50, our mean is going to be the same as the population mean, and our standard deviation is going to be $1,018.20. Okay, go ahead and try the same thing for parts B and C, and then come back. So you should have gotten these values for your standard deviation of the sample mean. When the sample size is 100, then you get a standard deviation of 720. The mean is the same. For sample size of 300, we get a standard deviation of $415.70, and the mean is the same. So what that's saying is they've got this population. I don't know how many mobile homes are in the population, but they've got this very large population. They've pulled sample sizes of 300 and a whole bunch of them. And when you pull sample sizes of 300, a whole bunch of samples of size 300, and you took the mean of every single sample, and then you took the mean of those means, you're going to get 65,100. And then if you did the standard deviation, you're going to get, of all the samples of size 300, you're going to get $415.70. And then for 100, same thing. If you did a whole bunch of samples of size 100, and you found the mean of every single sample of size 100, and then you found the mean of those means, you're going to get 65,100. If you did standard deviation, you'll get $720, and so on. So I wanted to point out that it's not 100 samples, not necessarily. I mean, it could be, but it's not 100 samples. It's samples, however many samples, of size 100. So every single sample in our distribution has 100 homes in it. So I have sample number 1 has 100 homes in it. Sample number 2 has 100 homes in it. Sample number 3 has 100 homes in it, and so on. And then for samples of size 300, that doesn't mean I have 300 samples. It means I have however many samples of size 300. So sample number 1 has 300 homes. Sample number 2 has 300 homes. Sample number 3 has 300 homes, and so on, all the way down to however many samples they draw. So I just want to kind of show the difference between that so that you understand what they're saying when they say sample size of 300 means that they pulled 300 homes, 300 different homes for each sample. So that goes back here to the basketball players. This was a sample size of 3 basketball players. So each sample represents 3 different players. So when they say a sample size of 300, that's a lot. That's so big. Each sample would have 300 homes in it, different homes. So hopefully that helps clear that up a little bit. On part D, I want to talk about what happens to the standard deviation as the sample size gets larger. So look up here, we went from 50 to 100 to 300. What happens to your standard deviation? It's getting smaller. So as, n gets larger, our standard deviation gets smaller. So what does that indicate? Let's think about for a minute a normal distribution. In our normal distribution, we have our mean in the middle, and then we have on the outside of the mean, we have 1 standard deviation above, 1 standard deviation below, 2, 3, and so on. So if 1 standard deviation is $1,000, the mean's in the middle, 65,000. $1,000, each standard deviation is $1,000. It's going to be kind of spread out. And then my sample sizes get larger. Now 1 standard deviation is $720. That's going to be less spread out. And then even larger sample size of 300, 1 standard deviation is like basically cut in half, only $415. Now we're getting closer and closer and closer. So as n gets larger, our data is going to be clustered closer and closer and closer to the mean. And so we're getting more accurate information. If our population mean is in the middle and our standard deviations are getting closer and closer and closer to the mean, then our data is getting closer, it's clustering closer and closer and closer. We're getting more accurate information, and it's all going to be clustered closer to the population. So when the sample sizes were smaller, they were kind of, our data becomes a little more spread out because of the $1,000 standard deviation. and we're going to get farther from the mean. Then we make our sample sizes larger. It cuts that standard deviation down. Now we're going to be less spread out. With a smaller standard deviation, we're less spread out until finally we have a sample size of 300. That's even less, even more less spread out. That was weird wording, but you get my drift. So I just kind of want to show the importance of that larger samples are going to get you more accurate information. It's going to shrink down that standard deviation. It's going to shrink down the error. It's going to shrink down all the inaccuracies, and you'll get closer to population mean. So that's all I have for this lesson. It was a long one, but I hope you enjoyed it. If you have any questions, please let me know, and I'll be more than happy to help.